Welcome to a lesson with Dr. Powell. Let's take a look at an example of rewriting a transformation that happens in regular standard coordinates, such as this one, um, um, rotating clockwise by 90 degrees. And let's suppose that we want to think about that in terms of a new basis, A, B. Um, So we have a skewed coordinate system determined by these two vectors, A and B, um, looking something like this. So we have a vector let's see, one, -1, so it's down, A is down like this, and B is 1, 2, so, B is going upward like this. So you have some kind of skewed system with some skewed coordinates of some sort or other. And within this coordinate system, we want to be able to take a vector in here that's described in AB coordinates, such as like the vector 1, 1, for instance, in AB coordinates is the same thing as saying A plus B. Like this 1 is referring to the E1 of AB coordinates, which is A. And this one is referring to the E2 coordinate of AB coordinates, which is just B. So these are like behaving like E1 and E2. We're like pretending that A and B are E1 and E2. So we want a matrix that pretends that, right? That pretends that that the coordinates we give it are actually E1 and E2, but that they're in terms of A and B. And we want to know what rotation by 90 degrees would look like in this coordinates, in these funny coordinates with A and B. Like, so basically what we're doing is we're taking a linear combination of A and B, and we want a transformation that says, what are these coefficients going to turn into if I rotate the whole plane by clockwise by 90 degrees? Like what's that coefficient going to be? And what's that new coefficient going to be? And I just want to keep thinking the whole time about as coefficients of A and B, but I notate those in a vector format as follows. Like this 1, 1 would mean A plus B. So that's kind of what I'm after there in that case. Okay, so if I keep, so let's look at how we're going to do that. All right. So first of all, we need a change of basis from AB coordinates to standard coordinates. Now this one right here, we just simply get by thinking of, okay, we want, so the notion of pretending is like a transformation. That's what this is. Okay, to begin with, this is like pretending. So we're pretending right now that our coordinates are E1 and E2 are really A and B. And then we want to stop pretending for a minute. So not pretending. And then we want to rotate, perform that transformation. And then we want to pretend again. Now, the process of going from pretending to not pretending is a linear transformation. And it's simply as follows. You put in 1, 0, which we're pretending to be A, and then we say that it's A. All right. That's the image of E1. E1 is in pretend land is A, and then it comes up here to real land. That's what A really is. E2 will go to this, right? E2 is where we're pretending that E2 is B, and it goes to what B really is. So the not pretending from pretending is a linear transformation. Now we put that into A, and then we want to go backwards from not pretending to pretending. And that would just be the inverse map or the inverse function of what we had over here. So we need to find an inverse to B. So we can compute the inverse to B. If we did, we'd get this. We find B, we have it right here. And then we have A. And then we work this out and we have this matrix. All right. Now let's take a look at an example of what's going to happen with this. So suppose we want to rotate by, we want to rotate 3, 2 in AB coordinates. How would we do that? Well, we think of 3, 2, right? When we plug it into this function, and we end up getting this or this. In other words, we can actually see what this looks like in standard coordinates if we wanted to. So 3, 2 in standard coordinates is 5, 1, and notice that it actually rotates to 1, -5, and that's exactly right, because if we change what we rotated by in AV coordinates back to regular coordinates, we get 1, -5 again. But so in pretend land, we know that this is what we have. This is what we've just figured out. We have figured out that 3a plus 2b has changed into one. Let's see, it looks like 7/3 as a, and then minus 4/3 b. All right. So rotation by 90 degrees clockwise produces this effect on A's and B's. Okay, where A is a vector, B is a vector, and they're adding like this is linear combination. It changes to this linear combination, and we've seen that because we have a nice matrix right here that'll show us how that happens. Thanks for watching.